All right, today we're going to look at polynomial functions. We want you to be able to evaluate polynomial functions using function notation and also identify the general shape of a polynomial using something called the degree and the end behavior of the graph. So this first one says the cross section of a honeycomb has this pattern with one hexagon surrounded by 6 more hexagons and so on. Surrounding these is a third ring of 12 hexagons. Keeps going. The total number of hexagons in a honeycomb can be modeled by this function shown here, where R is the number of rings and f of R is the number of hexagons. Find the number of hexagons when R is 4 and when R is 12. Okay, so if we want to figure out in the fourth ring how many hexagons are going to be, we want to plug 4 into this function. So anywhere there's an R, we want to replace that now with a parentheses and then plug in the value, in this case 4, in for that and evaluate this function. So go through now and use order of operations and see what you get. So we want to evaluate parentheses first. Well, our parentheses are simplified. Then exponents. We do have exponents here. So right here in this term, before we multiply by 3, we need to do the exponent. Exponents always come first. So multiplying that out, we got 4 times 4, or 4 squared is 16. So that's going to be 3 times 16 there. Minus, there's no more exponents. So now we need to go through and do the multiplication. 3 times 16 is going to give us 48. 3 times 4 is 12, plus 1, so 48 minus 12 is 36, 36 plus 1. There is going to be 37 hexagons total in that fourth ring. Okay, why don't you pause the video, see if you can do the same thing now with 12. How many hexagons in the 12th ring? All right, let's see what you got here. If you do the exact same thing now, just putting in 12 instead of 4, we have this, and you should evaluate, make sure you do exponent first again, it should evaluate to 397 hexagons if you did it right. Okay, that's function notation. You guys learned about that a little bit in a prior unit. You should be able to apply it again now when we're doing these problems. All right, some other terms we're going to be looking at today. Polynomial in one variable. We say a polynomial is in one variable when there is only one variable in the polynomial, so you can't have multiple variables. You got to have one variable throughout the problem. Also, polynomial in one variable means the variables are all going to be in the numerator. There should not be any variables in the denominator of a fraction. The second term, degree, we've talked about this one a little bit already. It's the largest degree of a monomial term in the polynomial. So if you look at all the different exponents, whichever one's the largest one, that's the degree of the polynomial. And leading coefficient, that's the coefficient or number in front of the term with the greatest degree. So whichever one has the biggest power, the number in front of that variable is the coefficient, and that one would be the leading coefficient. Okay, so let's see if we can find some of those things on a few polynomials here. So they want us to state the degree and the leading coefficient of each one here, if it actually is a variable in one polynomial. Okay, so the first one, let's check. Is there just one variable here? Yes, in number 1, only x is the only variable, so that's good. Is there any variables in the denominator? Nope, we don't have any fractions. So this is a polynomial in one variable. So let's state the degree now. What's the biggest power we see here? Well, we got 4, 2, 1, and 0. So the biggest one is 4. This one's degree 4. Okay, what's the leading coefficient then? Leading coefficient would be 7, since that's the number in front of the biggest degree. All right, number 2. Is it a polynomial in one variable? Well, let's look. Is it just one variable? X? Ooh, we have both x and y here. So this one we would say is not a polynomial. in one variable. And the reason is we have two variables going on here. All right, the last one, number 3, looks like x is the only variable. Is there any variables in the denominator? Uh-oh, yes, there is. So we would also say this is not a polynomial in one variable. And the reason we would say on this one is that there is variables in denominator. You can't have that in a polynomial in one variable. Okay. All right, so those are some things you're looking for, some terms that you might run into. All right, next one. They want us to, again, do some function notation here. Now, before we plugged in numbers, now we're going to be plugging in maybe things that aren't necessarily just whole numbers into the function. So on number 4, they want us to find what is the function at b squared. So before we had like a number here like 3, and we just would go through and plug 3 in everywhere, and we would evaluate it to some number answer. But now we don't. So we're still going to plug in what's shown here. It's just that you're not going to get a numerical answer. So wherever there's an x, we're going to substitute b squared in for that. So we're going to put b squared in for every x in the problem. Now we want to evaluate this. So we want to go through and just try to simplify it as much as possible. Well, first thing that I see right here, we need to evaluate this. What do we do when we have power to a power? Well, power to a power, we should multiply. We looked at that earlier in the unit. So we're going to have 2b squared to the second power, b squared times b squared is going to be b to the fourth power. Plus, okay, 3 times b squared, there's really nothing to evaluate there. Those parentheses aren't doing anything. Minus 1. So now we just want to check, can we combine any like terms here? Nope, there doesn't appear to be any like terms. That's our answer. That's as much as we can simplify. That would be the solution. You're not going to get a numerical solution unless you plug a number into the function. All right, let's try another one here. Number 5. They want us to evaluate this function g at c plus 2. Now also notice there's a 2 here. So that means when we're done, we also need to times this function by 2. So, or times multiply the result by 2. So we're going to have 2 times whatever this is once we plug in c plus 2. So now we want to plug c plus 2 in for x and see what we get. So we're going to have c plus 2 squared minus 4 is what you get when we substitute that in. All right, now we got to evaluate this. So what is this going to simplify to? This is the most common mistake with exponents that students make in this part right here. Okay, you got c plus 2 squared, and a lot of people just go, oh, we can just go c squared, and then 2 squared is 4. No. That is not equal to c squared plus 4. Okay, you can't take the power to both things when there's more than one term here. Okay, think about what it means when you take something squared. When you square something, there's 2 of them. So what this means is we got c plus 2 times another c plus 2. We're going to have to go through and multiply it out this way by distributing, or use that FOIL method to get the answer, because there's more stuff than just c squared plus 4 there. So if we multiply that out, we got c times c is c squared. Let's multiply the outside things. C times 2 is 2c. Multiply the inside things, that's another 2c. And then the last things, 2 times 2 is 4. So that c squared and 4 that we had before is there, but there's also these 2 terms that we didn't have. That's why you can't just square both things. All right, and we still got this other little minus 4 at the end. So now we want to simplify that and see what the answer is here. These are some like terms we can put together. These are some like terms we can put together. So we got 2 times 2c plus 2c is 4c. 4 minus 4 is 0. We don't need to write anything for that. And now if we multiply both of these by 2, the answer is 2c squared plus 8c. That would be the answer they're looking for in that one. Those are not like terms. We cannot add those together. All right, some other stuff we're going to look at then besides function notation is some things you should notice when graphing polynomial functions. So in this little picture here, we have some different degree polynomials. We've looked at the first three already in prior units, okay? Anything that's degree 0, okay, meaning you don't have any powers of x, okay, that's just going to be some kind of function like y equals 6 or y equals -2. If you graph out any degree 0 function, like y equals 6, that's just a horizontal line going through the point 6, and every graph is going to be constant like that. So any degree 0 function is just a horizontal line. We've looked at those before. We've also looked at degree 1 equations before. That's where the biggest power of x is going to be 1. Any degree 1 function, that's a slope-intercept line, where the degree of x is 1. So you're going to just have some kind of y-intercept here of b. You're going to have some kind of slope on this line of m, and it's going to be a straight line, just not constant. It's going to be either increasing or decreasing. We've also looked in prior units at degree 2 equations, which are quadratic functions. Those are functions that look like this. Ax squared plus bx plus c. The biggest degree is 2. That's why it's degree 2. So anytime you graph one of those, you get a quadratic or a parabola shape to it, okay, where c is your y-intercept, and then we looked at how you can find the vertex. That's this point. And your vertex is either maximum or minimum, and you can find that by doing -b over 2a. And then also we looked at how you can find solutions. Those are the points where it crosses the x-axis. And you can find those by factoring, or you can also find the solutions by doing quadratic formula, which you guys did in prior units. Okay, so those are all things we've looked at so far with those three. The ones above degree 2 we haven't really looked at. So a degree 3 equation looks like this. A degree 4 is going to look something like this. Degree 5 is something like this. Now, if we look at all of these together, there's hopefully some patterns that we can see when looking at these. Okay, one pattern we can look at, and there's kind of a hint down there, is to look at the number of times that these graphs change direction. Okay, how many times do these graphs change direction? Well, the first one, or first two don't. Let's look at the degree 2 one. How many times does this change direction? One time. Right here it changes direction. How many times does this one change direction? Once there, so 2 changes of direction. This one has 1, 2, 3 changes of direction. This one, 1, 2, 3, 4 changes of direction. So what do you notice about the changes of direction compared to the degree? The degree is always going to be 1 more than the number of changes of direction. So that is something that's always going to be true in graphing a polynomial. So if you want to help figure out what degree it is, look at the change of directions and add 1. So that's something you can write on your note sheet here. The degree is always 1 more than the number of changes of direction. Okay, so on any polynomial, that's always going to be true. All right, some other things. What we look at is what are the ends of the graph doing? Okay, the ends of the graph are what we call the end behavior. We'll come back to this in a second, but the end behavior of a polynomial, and there's room to write this on your note sheet, is the trend of f of x. F of x, remember, that's like y, or also that's also talking about what the graph is doing. As x approaches negative infinity and positive infinity. Negative infinity we're going to write like this. positive infinity, we're going to write like this, or just regular old infinity without the plus sign. Okay, now we got to talk about what does that mean. As x approaches negative infinity and positive infinity, if x is approaching negative infinity on a graph, okay, which side of the x-axis is negative? That's this side, the left side. So this means as you move left, what is your graph doing? If x is approaching positive infinity, the positive side of x is the right side, so this is talking about what's your graph doing on the right side. So we want to look at what is the graph doing as you go left, and what does the graph do as you go right. Let's go back to our pictures here. So on degree 2, if you look here, both ends are going to positive infinity. Okay, if you look at degree 3, the left side's going to negative infinity, the right side's going to positive. Degree 4, they're both going to positive infinity. Degree 5, the left side's going to negative infinity, this one's going to positive infinity. So what's a pattern that we see here? Even degree polynomials, the ends always go in the same direction, whether that both be positive infinity or they could both go to negative infinity. You guys have seen parabolas before that open this way too. Okay, so they're both going to go the same way though. Odd ones then, the ends go in different directions. Either one's going to go up and the other one's going to go down. So that's a way you can quickly identify it as even or odd. So if you see that both ones are going opposite, we know it's an odd one. Then you can look at the number of turns to see what the degree would be. All right, so we're going to see if you can identify then some of these graphs using that. So there's another little picture here, kind of takes you through looking at this. Okay, if you look at this graph right here, we should know right away, okay, same direction. That means it's going to be even. Okay, we see one turn. So that means the degree of this one would be degree 2. If you were going to state the end behavior of this one, okay, we see that as x goes to negative infinity here, so that's this side, x is going to negative infinity, that our graph is going to positive infinity. So we'd say f of x is going to positive infinity. On the other side, this is where x goes to positive infinity on this side. Our graph is also going to positive infinity, and that's it. So that's how you would state the end behavior. Okay, and there's some other examples here. If you want to go through, you can look at those. But we're going to take we're going to look at some other examples, see if we can state these here. So for each graph, we're going to state the end behavior, figure out if it's odd or even, and then state the number of zeros. We haven't really talked about that yet today, but we have talked about it in the past. So number 6, let's try to figure out, is this even or odd? Well, both ends here are going to negative infinity. Okay, so if they're both going same direction, we know this one is going to be an even degree. Let's see if we can figure out what that degree is now. So there is 1, 2, 3 turns. That means the degree is going to be one more. This is going to be a degree 4, and 4 is an even number, so we know the degree. All right, they also want us to now state the end behavior. We already identified it. Let's just state it out now. So the end behavior would say as x goes to negative infinity, that's the left side. What's our graph doing here? So on the left side, this is where x goes to negative infinity. What do we say our graph does? Our graph's going to negative infinity. On the right side, as x goes to positive infinity, looks like our graph is also going to negative infinity on that side. So that's how you would state out the end behavior. All right, they want us to do one more thing here, identify the number of real zeros. So zeros, remember, are also referred to as solutions sometimes, or roots, but really what they are is how many x-intercepts. So how many times do we see this graph crossing the x-axis here? Looks like this one has 2 real zeros. All right, let's take a look at number 7. On this one, both sides here looks like are going to positive infinity. We know from before that that means this is going to be even degree. What is that even degree? Is it 2, 4, 6, 8? What is it? Well, we see there is one turn here, right there. So the degree is one more than that, so this is degree 2. This is a quadratic. You get a parabola. All right, let's state the end behavior. This side is x going to negative infinity. This side is x going to positive infinity. So we would say as x goes to negative infinity, the graph on this one, f of x, is going to positive infinity. As x goes to positive infinity, that's the right side. Our graph is also going to positive infinity. All right, finally, how many real zeros? How many x-intercepts do we have on this one? This one has 0 real zeros. There are none. Okay, this one never crosses through the x-axis. The number of zeros can always be up to the degree. So we could have had on this one up to 2 real zeros. On the last one, on number 6, this one, since it's degree 4, could have had up to 4 real zeros. If this little middle part had gone down a little bit more, okay, then there would have been 2 more here. So the number of zeros always could be up to the degree. The zeros can't ever be more than the degree. All right, why don't you guys pause the video here, see if you can try number 8 on your own, see what you get. All right, let's see how you did. What are the ends doing? This one's going to negative infinity and positive infinity. Because they're different, this one's going to be odd degree. Let's see what that degree is. We got 1, 2, 3, 4 turns. Degree is always one more. So this one is degree 5. This one's going to be degree 5. Since it's degree 5, we could have up to 5 zeros later when we check that. All right, let's write out end behavior. Left side is where x goes to negative infinity. What's it doing? What's our graph doing on that side? Looks like it was going to negative infinity. On the right side, that's when x goes to positive infinity. What's our graph doing? On this side, that was going to positive infinity. Okay, last thing, state the zeros, and we just said it could be up to 5 since this is degree 5. Let's see how many there actually are. 1, 2, 3, 4. This one did have 5 real zeros. It can't have more. It could have less than. It can't have more than that. All right, why don't you try some of these out now on the practice.